Alright, similar to the first two energetics videos which I've created some time ago, right? I'm going to run all of you through some parts of section 8, which is actually the last part of the chapter on energetics. It's actually something that is very new to most of you because I do believe that in secondary school you have gone through things like very simple ideas like heat transfer, maybe enthalpy change, calculate very simple stuff. And to recap a little bit about what we did earlier on would be we are just trying to relate via a hair cycle all the different enthalpic terms together. Yeah, essentially that's the first 30 pages. Okay, and you are also introduced to the idea of calorimetry where you use some sort of like a coffee cup calorimeter, which you have done in practical 5 and 6 to run a simple energetics experiment to measure changes in temperature and then from there determine the limiting reagent and then you can calculate delta H. Okay, so it seems that the focus of delta H it's quite a lot from from 2 weeks ago until now. So now we are going to introduce to you actually two new terms. Okay, the first term is actually entropy. Okay, but entropy this term, right, is coupled with the word change as well. Yeah, so in this case, we are looking similar to delta H, which is a state function. Entropy is also a state function. Okay, I mean, I will not go into the mathematics because for those of you who are really interested in the origin of state function or path function for that matter, it's actually outside the scope of even H2 mathematics. You want, you can reread a lot more about it, either after your A-levels or during the holidays. Okay, but right now we just go straight into the business and just introduce you to the terms. Okay, so yeah, delta H, introduce the enthalpy change. Section 8, we are going to introduce you to this term known as entropy change, which is delta S. Okay, if you heard what I mentioned maybe in the earlier two videos, I mentioned that usually enthalpy change is something we focus a lot on in our discussion in secondary school. Yeah, but there is actually another important component known as the entropic component, that's delta S. So this is delta S I kind of talk about maybe sometimes in the tutorials I mention it indirectly. So that's the entropic contribution. Okay, and together delta H and delta S, we determine the Gibbs free energy changed. So Gibbs free energy change is represented by delta G. Okay, so we are relating delta G to delta H and delta S. Okay, so if you flip over a few more pages, you realize there's this relationship. Delta G is equals to delta H minus T delta S. Okay, yep. So yeah. So without further ado, I will just run you through the important idea about entropy change and Gibbs free energy change and how they are related. Okay, so I think first of all we need to understand the term spontaneous. Okay, so what exactly is spontaneous? I think the simplest thing I can explain to you about spontaneity, right, is if you are in the corner of a room, you spray perfume, and then maybe within 10 to 20 seconds, the other side of the room can already smell the perfume. So we say that the diffusion of the molecules responsible for the scent of the perfume, right, goes from one end of the room to the other end, or rather it gets spread out evenly. So this is what we call a spontaneous process. Okay, or another way to look at it is if I add, like if I have a cup of water, I add a drop of ink inside. So in this case, they are talking about dye. And then you notice that the dye or the ink will spontaneously distribute itself throughout the whole solution, so that initially it's very concentrated. Let's say it looks blue, and then after a while it will appear lilac. Yeah. However, you realize that the reverse doesn't happen. So that means that you will realize that if I give you a cup of water with the uniformly dispersed dye, right, it wouldn't on its own, right, concentrate itself into one region. Yeah, so the reverse process is non-spontaneous. Okay, and over many years or many centuries, scientists has been pondering over why this is the case, like why such things happen, etc., etc. Yeah. So again, as per the earlier lectures, I really urge you to go and look at the history of thermodynamics. I think they, 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 they are able, I mean, read about those scientists that came up with this concept. They will really give you a very good overview of all the ideas that you are learning. Although it overlaps pretty much a lot with physics. So those, I mean, some of you are not taking physics, but in biology, there's also a lot of process that are non-spontaneous, but because it coupled with another reaction that is spontaneous, the overall reaction seems to be spontaneous. We call this thermodynamic coupling. Okay, so yeah, I mean, I will not rattle too much on this, but yeah, so you get my point. What exactly is a spontaneous process? So of course, our lecture notes wrote it that it's a process where you don't need to continuously input energy, so it just happens. Okay, so yeah, so it's useful to actually predict if a reaction will occur spontaneously, you know, like when you put reactants together. So for example, you know that a lot of exothermic reactions such as combustion, once you spark off, once you put a light source in your combustion engine, and then the petrol will just burn. So that's what we call a spontaneous process, which happens on its own. And usually we associate it with exothermic reactions. Okay, but there are also endothermic reactions that are spontaneous. So for example, you know, sometimes when you dissolve a salt, especially nitrates, into water, and you realize that the solution turns cold. So does it mean that endothermic reaction don't like to take place? Actually, it's not true. Endothermic reaction does take place as well. Yeah, so they are spontaneous. So that means that whether a process or a reaction is spontaneous or not, right? It has nothing got to do with whether is it exo or endo. Yeah, of course it has got to do with it, but there is also another factor that will affect whether the process is spontaneous or not. Yeah, so that's why we need to introduce you to this term known as the entropic term. Okay, yep. Of course, now if you look at this particular paragraph, right, they actually describe a little bit of things to you. They actually mention that, okay, although the above two processes are endothermic, but they are common, they have one common features. The common features is that you notice that a solid state, right, eventually became 2.5 moles of gaseous molecules. So from 1 mole of solid, you get 2.5 moles of gaseous molecules. Okay, and then the one below, the solid actually dissolve to give you the aqueous ions. Yeah, so in chemistry, we say that when you go from a solid to a gaseous phase, or when you are a solid and then you dissolve to form ions, right? We say that it results in a system where there's a greater degree of freedom. Okay, so this degree of freedom actually is kind of favored because it allows, it gives you more rooms to diffuse, to move along. Okay, so this actually brings us to another expression. So we say that when you have a greater degree of freedom, that means that the energy become more easily dispersed, or you can say it's distributed. Yeah, so that is why later on you realize that one of the definition for entropy is that where when you go from when you increase the temperature of a gas, so for example oxygen gas, um, maybe at 200 kelvins, when you increase the temperature of oxygen gas to 300 Kelvin, we say that the entropy change actually increases or become more positive, despite the fact that the number of moles of oxygen molecules remains the same. Why is that the case? Because as we increase the temperature from 100, I mean from 200 to 300, the system become more energetic. Okay, but as the system become more energetic, we realize under the Maxwell-Boltzmann distribution curve that it broadens. So that means that the same number of moles of gaseous molecules, right, are able to access greater kinetic energy. Yeah. So that is one way we can look at it. Remember in your gaseous states, you learn about the Maxwell-Boltzmann distribution curve. As you increase the temperature, the Maxwell-Boltzmann distribution curve actually broadens. Yeah, so the broadening of the Maxwell-Boltzmann distribution curve allows the same number of moles of gaseous molecules, right, to access greater kinetic energy. So that means that there are more ways for energy to be distributed, okay, in the same number of moles of gaseous molecules. Yep. So yeah. So these are different ways we can sort of understand entropy. And then of course this particular paragraph talk about going from solid to gaseous, which I probably don't want to go into it as well. And then the dissolution also result in a more positive entropy change. Okay, so we have an ending paragraph here. So a change in the degree of freedom, which means the distribution of the energy of motion is a key factor affecting the direction of spontaneity. Yeah, so this is known as entropy change. That's one way of looking at it. This is not the only way. Yeah, but I think when our notes is written, this is one way where we try to position the ideas. Okay, so entropy change is entropy is represented by S, so this is known as absolute entropy. So normally at your level, you don't really write it as S, okay, but you write it as delta S. So we are interested more in the change. So in the change from the initial to the final states. Okay, so I think this needs no introduction. So the absolute entropy, we're talking about absolute entropy of solid is definitely greater than liquid and is definitely, sorry, solid is definitely smaller than liquid and it's definitely smaller than gas. Okay, so because of that, when you go from solid to liquid, which means when you melt, when the solid melts from the solid phase to the liquid phase, you would expect the entropy change to be positive. And at the same time, when you vaporize liquids from liquid to the gaseous phase, now the gaseous molecules have more ways where the energy of the system can be distributed from the motion of particles. Okay, so it's no longer being restricted to the volume of the liquids. Okay, so now you can say that as we go from liquid to gas, the entropy change actually become more positive. Yeah, because the gaseous system has a much larger absolute entropy as compared to a liquid system. Okay, yep. I think this is this probably this particular part might be something you want to take note of. Yeah. So many chemical changes of physical process are accompanied by a change in entropy. Okay. So if you go from an initial state where there are less ways to disperse or distribute energy to a final state where there are more waste, then you expect a positive entropy change. Okay. Then the other way around, when you have more ways of distributing energy to a final state where there are less ways, the delta S will become less than zero. Okay, but one thing you might want to take note of is that in the case of question, they usually will ask you for the sign of delta S. So when they ask you for the sign of delta S, right, you cannot say greater than zero or less than zero. Yeah, so this is not a correct way of answering. You have to tell us whether is it positive or negative. So basically read the question carefully. Yeah, if the question asks for sign of the delta S or delta H or delta G, make sure you write it as positive or negative. Okay, don't just say greater than or less than. Yep. Okay, 8.3, yeah, so this is the part that which I kind of like indirectly mentioned it earlier on. So predicting the sign of delta S for some processes. So for example, the change in temperature, this is the one that we mentioned earlier on. Yeah, so we have the same amount of particles. So as we increase the temperature from T1 to T2, you realize that the Maxwell-Boltzmann distribution curve broadens. So the curve broadens. So when it broadens, you allow this portion, okay, with a greater kinetic energy, you allow a greater number of particles being able to access the greater kinetic energy. So that means that now I have more ways, or the system have more ways to disperse this energy amongst the particles. So increasing temperature for the same number of particles actually increases the entropy. Okay, so it gives it a positive entropy change. Okay, so change in temperature is something that you need to be aware of. It's part of your syllabus. The change in phase needs no introduction. I think we have been talking about that since the beginning when we gave you examples. Okay, so I think this needs no introduction. Yeah, what you learn in secondary school, even Sec 1, you learn that a solid where you have particles vibrating about their fixed position, and then in a liquid phase, they are free to move within the volume of the liquid volume. Yeah, and then of course gaseous particles they are free to move anywhere. Yeah, so all this still remains, and I think you can easily predict that vibrating about a fixed position has definitely a much smaller degree of freedom as compared to the liquid molecules being able to maneuver around the liquid volume. And of course, when it becomes the gaseous phase, it can maneuver it can maneuver the atmosphere or any other areas where it can encounter. So that gives it the largest absolute entropy. Yeah. So phase change, so for example, from a solid to a liquid accompanies increase in absolute entropy, and therefore the delta S for phase change will become positive. Yeah. Okay. So that's something that you maybe want to pay attention to. Okay, so I think whatever I mentioned, it's actually in these two bullet points. So that's something you need to maybe highlight or think about. And in fact, I'm sure you can always clarify the tutorials. Okay, there's also the third point, which I think again needs no introduction when there's an increase in particles, especially gaseous particles. So in this case, you notice that in this particular equation, the number of moles of gaseous particles increases from 1 mole to 1.5 moles. So there's an increase by 0.5 moles per equation in this case. So therefore, positive entropy change. And of course, you need to be a bit careful because for the case of sodium azide, there's a solid phase here, so it begins with 0 gaseous molecule. It ends up with 3 gaseous molecules. So the number of moles of gaseous molecules actually increases from 0 to 3. Yeah, so entropy change is very positive in this case. Okay, usually when there's no change in the number of moles of gaseous molecules from the beginning to the end, right, you expect the delta S to be a very small number. Okay, it's likely to be a very small number. It's not going to be 0 because it's definitely not going to be 0 because the absolute entropy, which is not in your syllabus, okay, the absolute entropy of nitrogen, oxygen, and NO, right, they are inevitably different. So because they are different, even if you calculate, try to calculate the absolute entropy of N2, O2, and then you calculate the 2NO, you do a subtraction, right? You're going to end up with a number. But this number is likely to be quite small. So for that matter, to simplify matters, we say that it's close to 0. Yep. And then, of course, mixing as well. Yeah. So normally, mixing allows a positive change in entropy. So let me just give you a very simple example. So in this case, you notice that for H2, right, it occupies a volume V1, let's say for example, and N2 occupies a volume of another V1. So the total volume the total volume is 2V1. Okay. Now, if I remove this particular barrier, right, this particular barrier, you notice that for each hydrogen molecules, or for that matter, for each nitrogen molecules, right, after the barrier has been removed, right, its accessible volume, okay, accessible volume actually doubles in this case. Yeah. So when its accessible volumes doubles, it allows more ways to distribute the particles and the energy. What do I mean? What do we really mean by more ways to distribute the particles and the energy? So if you take a look at each of the nitrogen, right, we are looking at it based on the fact that it has a greater degree of freedom because instead of volume of V1. Now it has two V1 to maneuver about, and at the same time, um, right, because it has a fixed energy, okay, yeah, so at a fixed temperature, remember Maxwell-Boltzmann distribution curve, yeah, so that it has a fixed energy. So when it has a greater degree of freedom, so it's able, so that means that for the fixed amount of energy, right, the system is able to have more ways for the distribution of this energy. Of course, when we keep saying more ways to distribute the energy, etc., it seems very vague. What do we mean by more ways to distribute this energy, the energy? Okay, actually, there is no simple solution to this, to be honest with you, because if you want to go deep, you have to understand the concept known as statistical thermodynamics. But I can use a very simple illustration for you. So let's say, right, you have a pail. Okay, you have a pail here. And then you are given one ball. Okay, what okay. If you prefer just maybe a marble. Okay. How many ways do you have to distribute this marble in this pail? So actually it's just one way. Okay, so if you put a marble in, okay, I use another color, so the marble is here. So there's one way for you to distribute the marble in the pail. Okay, so how do you increase entropy? Okay, so one way is I add more pail. Because if I add more pail, right, now I have two ways to distribute the marble. The marble can either be here, okay, or I can distribute it here. Okay, or I can increase the number of marbles. I have two marbles. So if I have two marbles, okay, there are three ways in fact to distribute. One way is one each. Okay, second way, two on top. Okay, third way, two below. Yep. So you realize that if I increase the pail, then I will have more ways I can distribute the same number of marbles. Okay, or if I fix the number of pails, okay, I increase the marbles, I also have more ways to distribute. Then if you increase both, of course you have more ways to distribute either one. Yeah, so if you imagine the pail is like an energy level, and then the marble is like a quantized amount of energy. Yeah, so you get the idea. Okay, so that's really what we meant when we say that we have more ways to distribute. But again, I'm just using this very simple illustration to bring across this idea, so we will not go further into details. Okay, yeah. Okay, so expansion of gases, of course, you can understand that definitely there are more ways for the particles to be distributed as well. Okay, yep. Okay, okay. So this is an interesting scenario. So when the gas are mixed at constant volume, that is the volume available to distribute each gas particle is the same. Entropy does not change. Okay, the entropy does not change. So why do we say that? Well, I mean, you notice, right? I mean, to put it in a very simple manner, this is V1, this is V1, right? And we put them together, it's still in V1. So the accessible volume experienced by each or rather by each molecule, whether it's the blue molecule or is it the white molecule, right, is the same. So therefore, the entropy does not change. So therefore, delta S is 0. So looking at accessible volumes is one way of deciding whether there's entropy change. Yeah, so there is a pretty famous physical chemist in the recent years based in Israel. He actually came up with this concept known as the Shannon measure of information, SMI. So you can read about it. It's actually in the University of Israel. Yeah, he did a lot of studies on thermodynamics, etc. Okay, so I will not go too much into details as well. Yeah, so when liquids with similar polarities are mixed together, entropy increase. Yeah, I mean that explains why, because the volume nearly doubles, and then each solvent molecules will have more available volumes to maneuver. Okay, yep. And then of course dissolution of an ionic solid. I mean, I think this needs no introduction. If I dissolve, I generally I will expect the entropy to increase if you look at it from the perspective of the solid, because now the ions are more randomly distributed. However, uh, not to forget, water molecules also form favorable ion dipole interaction with water. And when the water molecules with the ions, sorry, when the water molecules actually surround the ions, right? Actually, the way they surround it is quite an ordered fashion, like they surround it nicely. So this may actually cause a local decrease in entropy. So whether dissolution results in a positive entropy change or a negative entropy change, it really depends. I mean, we can't say for sure. But of course, here we just say that, if the factor is the first factor, meaning um, the factor where your solid more free to move around the solution is a more significant factor, then of course the overall entropy change is positive. But usually that may not be the case. Okay, so so we'll need more exploration by looking at the data provided to us. Okay, yep. So so maybe we will bring you back a little bit to chapter 2. Topic 2, we say that the dissolution of a compound depends on the energy change. Yeah, so therefore, maybe I won't say we want to correct ourselves, but maybe now you need to know that there is another factor that can predict whether a compound is soluble. That is delta S. So we actually need both delta H and delta S to help us predict whether a solid is soluble or not soluble. Okay. Yeah. So with all this, I'm not going to go through the lecture exercise with you because I think largely I already love you to do it on your own and maybe check the answers that's uploaded. And as I mentioned in the earlier two videos as well, some of the lecture exercises already have available videos for debrief, so you guys can go ahead and look at them. Yep. And comes the most important expression now, that's called the Gibbs free energy. So yeah, it's worthwhile reading about this very famous scientist, Josiah Gibbs. Okay, so he came up with the Gibbs free energy expression. So that's delta G is equal to delta H minus T delta S. Again, students in the past like us, why is it minus T delta S? Why not plus T delta S? Okay, so again, I'll leave it to you to read the historical origin. But why is it minus T delta S? Is not a very easy question to answer because you need to perform a series of integration, etc. So we will not go into further details within the score. It's not within the score this syllabus. Okay, so as of now, maybe just remember this expression: delta G is equals to delta H minus T delta S. Okay, take note that similar to your enthalpy changes, the standard Gibbs free energy change comes with superscript here, which it goes something like a knot with a bar over. Okay, so this is a standard Gibbs free energy change. It's measured at 1 bar, 298 Kelvin. Okay, so yes, we use delta G to predict if a reaction is spontaneous. So if delta G is less than 0, reaction is spontaneous, takes place spontaneously. So the reaction is said to be exergonic. Okay, so important term. Delta G 0 equilibrium. So there's no, it doesn't favor the forward or backwards. Okay, so usually during melting and boiling, delta G is 0. So maybe you want to take note of this as well. Okay, delta G greater than 0 is not a spontaneous process. Okay, but the reverse will be spontaneous. So we say that the reaction is endergonic. Okay, so good to know these terms as well. Yeah. We deliberately keep this short because I think number one, for H2, this is the only expression. This is the expression you need to know under Gibbs free energy. Of course, it's technically a lot more in depth, but we're not going to go into details for H2. Okay, so we keep this to half a page. Okay, so of course, 8.4.1 we have exercise 8.2 and 8.3, which allows you to calculate delta G from delta H and delta S data. So I will leave it to you to do the calculation, but maybe what I can stress to you is that a very common mistake that students make is they forget to look at the sign, or rather not the sign, sorry, the units. So the units for delta H is actually in terms of kilojoules, but the units for delta S is in terms of joules. Yeah, so you have to be really, really careful when you calculate delta G, because when you calculate delta G, I'm just going to do this for you. Remember it's delta H minus T delta S, right? Okay, so in this case, right, do not just blindly write in the numbers like this. 825 minus 298, okay, then put minus 272. Do not just blindly write in like this. The reason why you shouldn't be blindly writing like this is because this minus 272 is actually in joules per mole per Kelvin. So it's in joules, this is in kilojoules. So you either multiply this by 10 to the power of 3, which I will advise you against because you're going to get huge numbers, or you simply just divide this by 10 to the power of 3. Okay, so remember this. This is a super common mistake that students make during exams. Okay, yep, so go and try, and I hope you can get some good answers, simple answers, and ensure that you understand what's going on. Okay, yep, so there are like a couple exercises for you to try. I think you should go through them. Okay, so there's a section 8.4.2 on the calculation of delta G reaction from delta G formation. This is actually quite similar because these are all state functions. Okay, these are all state functions. So we will just let you try via an exercise, but take note that delta G of a reaction can be calculated in a similar way using Hess law. Okay, so that means delta G, delta S calculation, you can apply Hess law as though you are calculating for delta H. Okay, because they are all what we call state function. Okay, yep. So there's a temperature dependence of delta G. Okay, so some question actually allows you to plot a graph. So you can actually, if you plot a graph of let's say delta G against, let's say maybe temperature, for example, temperature. Okay, you realize that the gradient and the y-intercept will give you delta S and delta H. Okay, so I'll leave that to you to go and work it out. I mean not work out over here, but you know, like that eventually you encounter question like this. Okay, usually we'll assume delta H and delta S not to vary too much with temperature, but of course this is usually not the case. Okay, so if you take a look at this particular examples here, right? At 298 Kelvin, of course, the delta H and the delta, the two delta H's at the different temperatures are about the same. Delta S also about the same. Yeah, and delta G varies by a bit. Okay, yeah. So sometimes in our calculation, because we are not very sure, we might just assume that the delta H and delta S value do not change appreciably with temperature. But of course, that is assuming that they are still in the same states. Whenever there's a change in states, then you realize that there is likely to be a drastic change in those values. Okay. Yeah. So this is what we are talking about. Okay. So different states. So you realize that you're going to end up with very, very different values. So do take note of the change in phase. So maybe I should highlight this, the change in phase. Okay, so the assumption that delta H and delta S remain roughly constant is not valid if there's a change in phase. Okay, so I think you need to take note of this. Okay. Alright, so yeah, there's an example 8.7 which again gives you some opportunities to perform the necessary calculations. So really, please work on them. Okay, and 8.8 as well. Okay, so I've covered most of the main points, and I think I'm coming to an end. I think there's two more parts which I thought I need to talk about. Okay, one is 8.4.4, which is the effect of temperature on the spontaneity of a reaction. So for a reaction to be spontaneous, the delta G should be negative. Okay, I think as we mentioned earlier on. Yeah, so you notice that the sign of delta G is dependent on the signs of and magnitude of delta H and delta S. Okay, now I'll leave you to work out the mathematics here because actually all these are all come from mathematics. Let me stress to you that you do not need to memorize this because in exam you can always decipher out on your own. Okay, you can always decipher out on your own. Uh, yeah, so if you blindly memorize this, that's where the problem comes. Then you're going to panic sometimes during exams. Okay, now before we go into this, right, I think we need to understand one important thing. The temperature is actually the thermodynamic temperature. Thermodynamic temperature. That means that it is actually in kelvins. So that means the number is always positive. Okay, so T is always positive. Yeah, so with this idea in mind, I think you can easily tell these two cases. Okay, what do I mean? Okay, if delta H is negative and delta S is positive, obviously delta G is always negative, right? Because T must always be positive as well. So a negative term minus of a positive term is always a negative term. So therefore, reaction is spontaneous at all temperature. I think we can understand this. And then of course the other way around, if one is positive, one is negative, then there's no way you can get delta G to be negative. So therefore, not spontaneous at all temperature. Yeah, yeah. So then the case will be interesting when we have minus minus and plus plus. Okay, so then one of them will be spontaneous at low temperature and the other will be spontaneous at high temperature. So when it's spontaneous at low temperature, we say that the reaction is enthalpy driven. Okay, enthalpy driven. So what do I mean by enthalpy driven? Which means the enthalpy change will drive the reaction forward. Okay, despite the fact that it leads to an over decrease in entropy. Okay, entropy driven means that the enthalpy changed. The entropy change drive the reaction. Yeah, because in the course of a reaction, right, the change in the number of moles of molecules, right, overrides the delta H term or has a greater effect on the enthalpic term. Okay, so these are some of the important phrase you can use when you address your answers in exams. Yep. Okay, I think I don't want to go through all this point by point because you notice that sometimes for the case of lecture notes, they're just written out to give you a bit of clarity. But really, it's not meant for you to go and memorize them word for word. You can always come up with your own terms. Okay, so that's 1, 2, 3, and 4. Okay, and I would like all of you to actually go through this example on your own. At 25 degrees Celsius, the delta G vaporization of water, etc., is actually 8.84 kilojoules per mole. So that means that the boiling water is not spontaneous at room temperature, which is consistent with our observation. Yeah, but the evaporation is. So vaporization versus evaporation, they are different things. So this delta H vaporization. Okay, of course, when you raise it to 100 degrees Celsius, delta G is 0. Okay, and then beyond that, delta G, the reaction becomes spontaneous. So that means that this particular system, right, is actually driven by the temperature. Okay, so that's why we have this figure called effect of temperature on spontaneity of boiling water. Okay, yep, and then this is followed by a lecture exercise here for you to look at whether the reaction is spontaneous at high or low temperature, etc. So I think I'll leave you to work through them. It's important to get yourself familiar. Okay, and of course, the final part is the limitation of using delta G to predict the spontaneity of a reaction. Okay, so what's the limitation? I think number one, under non-standard condition, sometimes you don't know how delta H and delta S will change. Yeah, so when that comes into the picture, you must actually calculate the delta G and the non-standard condition. This kind of question is not so common, I have to say, and yeah, because there are a lot more other details you have to look into. So normally, if you are required to do any of these calculations, you'll be given some clue to help you deal with it. Okay, so normally you can kind of like assume that whatever you need will be given to you, and they are usually at standard conditions. And of course, finally, all-time enduring examples, diamond to graphite. Yes, although it is thermodynamically feasible to actually convert diamond to graphite, but in reality, it doesn't happen on its own. The reason is there's this factor known as the kinetics consideration. Okay, so what we are trying to say here is that although the reaction may be spontaneous, but it may not occur after all. The reason is because the activation barrier or the activation energy may be too high. So if the activation energy is too high, then the fall reaction will not go. Okay, or it will take a long time for it to be overcome. Yeah, that is why right after this topic, the next topic you're going to learn is actually what we call chemical kinetics. Okay, or reaction kinetics for that matter. Yeah, so kinetics is another area that you need to look into when you want to decide or study whether a reaction is likely to go forward or no, or go backward. So there are two considerations when we are trying to decide if a reaction is likely to happen or not likely to happen. Okay, one is the thermodynamics consideration, which means we are looking at delta G. Okay, another consideration is actually the kinetics consideration, whether the reaction is fast or slow. Okay, so yeah, so that will be I think the end of the energetics chapter. I hope I have pointed out to you some of the key concepts that you will find useful in your revision. So yeah, just take note of them, and you realize that this chapter is very heavy on calculation. So just make sure that you get enough practice, especially your tutorials and in-class exercises. And yeah, I mean, and you're good to go and move on to the next topic, which is on kinetics. Yeah. Okay, so both are as important. So these are two very fundamental physical chem topics that are very important, together with the topic on chemical equilibrium as well. Yeah, so this will form the bulk of the topics you probably will need to be very good at before you sit for your promotional exams.